We start out with a question here. I got a piece of red chalk. Let's assume this carries a charge of 5 times 5 microcoulombs. Okay. My first question is, how much flux does that produce through or if you prefer, well, this big body. Okay. Well, people don't give me an answer. Okay. So now I say, and I think you can see this, it's just kind of sitting right here, right at the base of the board. Okay. How much flux is there through the plastic for this cap? Total flux produced by charge. Or pi KQ. That's why it's been introduced in the transition problems. That's something we've used several times. We really need to lock that in. Okay. So theoretically, that should be locked in so we can talk about applications of this idea. Okay. And you should understand the flux through a sphere, through a cylinder, or through a plane, charged plane. Okay. Because I'm going to assume that we can do that. And then we're going to look at some other situations that are a little bit trickier, like one I just posed for you. Okay. So you can think of that as the charge here produces this much flux. Okay. Now the question is, what fraction of that flux penetrates this board or this system of boards? Okay. So what fraction of the total flux do you think penetrate background there? Okay, so kind of give you a hint here. Field lines just give the direction of the field. So field lines are going to extend to the right and left of the charge, right? They'll extend up and down, and they'll extend in every direction. Let's just go ahead and divide things up with a bunch of field lines. It's probably enough to get the idea. Okay. Now let's assume that this continues on. It goes up pretty high. What fraction of the field lines, what approximate fraction of the field lines penetrate that surface? Okay, well, if the surface is infinitely high, but stops here, doesn't go down here, then every field line in the first quadrant is going to go through this surface, right? And the field lines are equally distributed because they come from the same charge. You get the same number of field lines in the first, second, third, and fourth quadrants, right? So that would be 1/4 of it. Okay. Okay. Okay, so I put this hollow cap top of my chart. What fraction of the field lines that emanate from that charge are going to go through that cap? Okay, well, fortunately, I got a quick answer here, and somebody said 50%. Everybody else kind of nodded. So I think that's what everybody was thinking. And then, a person said 50%. No, maybe all of it. Because all of a sudden, he started thinking about extraneous assumption. There's no part of this thing that goes below this plane. Okay. Now, if I had half a cap here and half a cap underneath it, then it would catch all of them. Except maybe those that leak out the little gap between them. But if there's no gap, it's going to contain them all. Okay. So is this difficult? Now, if that's 10 microcoulombs, 5 microcoulombs, so you know what K is and you know what pi is, you can figure out the flux and the flux density, right? Okay. Well, now, if this surface has an area of, let's say, 30 square centimeters. Okay. So that's a 30 square centimeter area. And what's the average electric field due to this 5 microcoulomb charge? So we got 5 microcoulombs. We have this gap here. There's our 5 microcoulomb charge. Surface area, let's say 40 square centimeters. What's the average value be on that surface? Okay, now the numbers are easy enough, but some people think numbers better than others, and everybody should be able to think this at this point in the course in terms of symbols, right? But just say, okay, in general, we got some area here, and we got some charge here. Okay. And this surface here is intercepting half the flux because, of course, you know, flux comes off like this. And so forth. Okay. So half the flux, the upper half of the flux, goes through this surface. So got charge Q, surface area A, surface intercepts half the total flux. What's the total flux? Start with what's the total flux? And then what does flux mean? Okay. Now, we're getting hung up on things that everybody should know from the transition problem. Okay. First of all, the 4 pi KQ, that should be locked in so that you never forget it by now. Okay, you had a half the semester, more than half the semester at this point to lock these things in. And the problems, be able to do these problems. If you don't know that the flux is 4 pi KQ, you can't do the problems. Just the transition problems you're going to be testing on next. Okay? So make sure you're locking these things in. Now, you did say, okay, well, half the total flux is then going to be half of this. So we did get that far. So that's a step. Now, what is the meaning of flux? So we have the question. What the flux is flux. Okay. What's this flux? This is flux. That's not quite grammatical. So I'm bordering on saying things I'm not allowed to say. So at least not in class. Okay. But that's where we are. And we shouldn't be asking that question. We should know what flux is. Use phi sub B, phi sub E for the flux of an electric field. Phi sub B for the flux of a magnetic field. You should know already that the rate of change of the flux of a magnetic field is equal to the potential difference around the loop. That should be locked in. We've used it. We've demonstrated it in the lab. Okay. Lock these things in. Okay. So flux is, I'll do this. Delta flux is electric field dotted with delta A. And E dot delta A means E perpendicular times area. You can work out your multivariable calculus to the point where you know that. It's not even multivariable calculus, it's pre-calculus. Dot product, meaning of a dot product. Okay, but if you want a picture, area increment, here's a unit normal, and here's your electric field. Area increment, dA, or delta A, would be the normal vector times the area. Okay, that's what an area increment means. E dot N is just E cosine theta. Theta is the angle between the electric field and the normal vector. In this case, in which there's 30-degree angle between here and here. Okay. If the electric field is parallel to the normal vector, so that you maximize the amount of electric field through the area increment, you're going to get just E times A. C perpendicular, E is perpendicular, so E perpendicular is D. Okay. Then, of course, you got to take signs. It either could be a positive flux or a negative flux. Then we're looking for positive charge or negative charge or whatever. Okay. But whatever your charge distribution dictates. That's what flux is. Asking for the average value of E on the surface if we know the area of the surface. Okay. Now, we actually don't know necessarily what the average electric field is on the surface because we don't know the angles with which the flux from this charge penetrates various parts of this surface, right? Because the electric field always makes an angle for this thing. However, we get a meaningful average perpendicular component of this. Make this statement. Okay. So the average is this. Okay, you can't say much more. This surface is not symmetric with respect to the charge. Now, if the surface was a hemisphere with area 40 centimeters, then what could you say? What? Forty centimeters squared, 40 per centimeter. Uh, the Q is at the center. I don't know why I said I didn't hurt. Steel tunnels in the line for us. Okay, now in this case, your picture, and everybody drew the picture rather quickly. Look good. Pictures really. Here's your charge Q, and here's your hemisphere. Okay, and here are your field lines. Your field lines all intersect the hemisphere like just basic 8th grade geometry. In a radial lines are perpendicular to the circle. Okay, hemisphere is not your circle. So your average electric field is 2 pi kq over A, not the average perpendicular electric field, because the electric field is perpendicular. And also by symmetry, it's uniform. Okay, well, let's kind of all slop around here. It's constant by symmetry. You know, I never know where you're going to go with this stuff. So no excuse for having a sloppy board, but it does have to evolve along with what you see. I have to tell you. Okay. Okay. So stuff like that. And that should be helpful to you. There are plenty of other configurations I could give you. But the most basic ones are the ones you encountered in the transition problems, where you have a line charge and a cylinder around it. You know, here's a line charge. Here's a cylinder. Total charge inside of here is just the charge density times the length of the cylinder. So total flux through the cylinder is just 4 pi k times the total charge in the cylinder. And from there, you can figure out the electric, more detailed symmetry and so forth, but they're all, I think, well addressed in the transition problem. So you really want to look back at the transition problems, make sure you have that down before you read the book. Or read the book, maybe it all comes back to you. Okay? The problems that you get in the chapter are problems that reason out by this sort of geometrical reason. And you'll always have some sort of symmetry. Keeps the electric field perpendicular Well, not always. There's one really neat problem in there where you gotta really see something. So, anyhow, that's kind of stuff you gotta know. Um, so I'm trying to think where we'll go with this. Okay, yeah, there's another situation, book tells you about it. And it is kind of the motivation for this thing. You got a conductor here. Okay. The electric field inside a conductor has to be zero. I've mentioned this before. It has to be zero because if it wasn't zero, then the charge carriers inside the conductor would redistribute themselves. And they redistribute themselves so that inside you have no electric. Okay. So you can read that book's argument, but it comes down to what I just said. If there was an electric field inside here, and of course, this is just some conductor in a steady state. You can get an electric field in a conductor. You can put one terminal of your battery here and the other here, and now you got an electric field through there, and you're going to have a flow of current, right? But you take that battery off, and the field disappears, and the charges almost instantly redistribute themselves, so there's no charge inside. Now, if the conductor has been charged up, that's pretty easy to do. I've got to be careful. I really injured the shoulder yesterday, but the armpit still works. Okay, so I'm getting charge in this thing. There is charge in this. Then when I touch this here, this thing becomes charged. For an instant, then the charge goes into my fingers and equalizes. But if this thing was being supported on an insulated stand, then this thing would attain a charge. And we'd have a constant charge density on the surface. Again, if your charge density isn't constant, then you have an electric field causes the charge to move around until it is constant. Okay? So on a conductor, an isolated conductor, I'm not even going to mention the details of it, you can read them. Okay? On a conductor, say all excess charge is on the surface. If there's any excess charge inside, then you have a non-constant charge density inside, and it readjusts. So all the charge gets chased to the surface, which is why, incidentally, you're fairly safe from a lightning strike if you're inside a metal vehicle. You get all kinds of charge coming down there, it'd fry you 100 times over if it all went through you. Okay? But it doesn't penetrate inside the car because the electrons repel each other to the maximum possible distance. So all the charge is on the surface of the car and quickly then goes into the ground or comes out of the ground and goes up to the clouds, which is more common. Okay? Does that make sense? It's a powerful image. So you got this conductor. Now, your car is a hollow conductor. If your charge was a solid chunk of metal, you would not want to be part of it. Okay, but right now what we're thinking is it's going to be a cylindrical shell or conducting shell, or it could be a solid conductor. Doesn't matter. If it's a shell, it does have an inner surface and an outer surface, and the outer surface is where the charge is going to go. It's not going to even touch the inner surface. Okay. At least not in any reasonable time frame. Within nanoseconds, all the charges on the surface, within nanopicoseconds, probably. I haven't figured it out. Real quick. Okay, so there's the point. Now, my question is, you have a constant surface distribution. Density sigma, and I shouldn't have to tell you that's charge per unit area. Okay. So now my question is, what's the electric field at the surface? I'll say very near. Large on this, you probably don't want to touch it. What's the electric field very near the surface? Okay. Well, let's pretend this thing is cylindrical. Okay. And we put it on the surface. Then how much charge is inside it? Well, it has cross-sectional area A, CS. And we can do this. We can take any tiny segment of this conductor. Surface. Then the conductor goes on like so, whatever the shape of the thing is. But here's a tiny region of the surface. So what we're going to do is we're going to do a prism, rectangular cylinder, like so, above the surface, and a little bit below the surface. Okay. Say this thing has area A, and of course, that means the part on the surface, but now we put this prism around the surface, right? So that this thing penetrates through to the other side of the surface. You can't see that, but if here's your surface, then this is on top and also another part on the bottom. The field is at every point perpendicular to the surface. So here's a prism. Cylinder, depending on whether this thing has lines for its boundary, like a square or an octagon or something like that, or some irregular multilateral, okay? Polygon, yeah, polygon, polygon. Or if it's got a smoothly curved surface, then you call it a cylinder. And it's got a little bit of both. You can just call it whatever you want to. Okay. I'm not sure there's a name for that. I'm sure there is. I don't know. So what's the flux? Cylinder. Flux is always now your X uses probably Qn divided by epsilon naught, but I'm going to use 4 pi K. Q sub n means charge inside. So how much charge is inside this prism? You got all the symbols there to tell me. Okay, well, we got around to it. It wasn't too awful bad, but somebody said something like charge over area. Okay, well, that's an important thing, charge over area. But what is charge over area? Well, that's your surface charge density. That's sigma. So this charge divided by this area is sigma. Therefore, the charge is sigma times the area. Lock that in. That's got to be second nature. You don't want to have to sit around for 5 minutes to think through that. Maybe the first time. But after that, you probably want to avoid pain and you'll lock it in. Okay? So it's 4 pi K sigma A. Now, how much of that flux goes out the top? How much of it goes through out the bottom? Well, at this stage, I've set the whole thing up. Read about it. Okay? Because it tells you, I think there's a whole heading in your chapter. And you can pretty much scan the chapter, especially to the extent that you've mastered the transition problem. Okay. I'm going to shift gears now and talk about potential. And I'm going to advise you that, next week we'll be talking about electric potential and capacitance. Okay. So I'm going to talk a little bit about potential. We already know that if you divide the potential difference by the length of a wire, you get the electric field. Okay. So in a wire, say in a resistance wire, any wire is a resistance wire because it has resistance. The resistance wire, we're talking about a wire where we can actually measure the resistance and we've done in lab. Okay. How do we measure the resistance? Potential difference is E times L. Units are newtons per coulomb times length gives you joule per coulomb, right? So potential difference is just a measure of the energy it takes to move a coulomb from one point to another. Or the work done by the field as you move from one point to another, depending how you set it up. Make sense? Remember this? You thought about this? Okay. Can you relate it to things that we've seen in lab? Well, you want to think about it. Okay. So now I'll jump. I'll use V for potential difference. If your voltage is E times L, or A to B of E dx, then dV dx is the electric field. Okay. It's the rate at which your potential changes with respect to position. Or okay, del V equals E. What's del V? And this just generalizes this. Now, everybody has now seen this in multivariable calculus. Okay. Those who are in multivariable calculus right now are working with it as we speak. Okay. And your book uses this notation, but there it is. You're going to see that in the chapter. But it's pretty simple, especially if you have a multivariable calculus background, as everybody here does. Whether they have it or not, that's it. Is it 4 pi k q over r? Or is it negative 4 pi k q over r? type P here. Then what is the potential? Now, the potential of a point charge is relative to infinite separation. So it's equal and opposite to the work done by the net charge, or by the net force, right? If I go from here to infinity, assuming a positive charge here, positive Q, and my force is in this direction, and my R goes from here to infinity, could go along any path, just assume it's a straight path away from Q. Okay. Haven't defined conservative vector fields quite yet, and multivariable calculus, but we don't require the knowledge of multivariable calculus anyway. From here, infinity is positive, right? So the work done by the net force in going from here to infinity is positive. By analogy, the work I do to lift that concrete block is positive as I move away from the source. Okay. So you want to reason it out in terms of the idea that potential difference is equal and opposite to the work done by the net charge. Okay. So anyhow, if we use this expression for the potential, you can still puzzle over that positive later. And go back to the idea of the dipole. So let's say we've got a dipole like so. Where the distance between the positive and negative charge, we put the positive charge here and the negative charge here. Where the distance between these is 2a. Okay. Let's take a point P, the y-axis. We'll call that P1. On the y-axis. And the little ambiguous notation I used here. This is my R. Okay, so the R we're using here is the separation between these. If we have an R axis along here, which we often use, then I'm just invoking what we did to integrate and find the expression for potential. Okay. So don't take this R as being related to this R. R is the separation between the charge and the point. Okay. And that's the R that goes into this formula for potential. So what can you tell me about the potential at this point? Well, you get to add the potential this charge to the potential due to this charge, right? How does potential due to this charge compare to the potential due to this charge? Well, aren't they equal and opposite? If they add up to zero? We'll call this plus and minus. Okay. Now, what if we have a point here's our x-axis. Let's say that P2 is at the point x, 0. What's the expression for the potential due to this dipole? Position is x, 0. This position is implicitly from everything's been written down is a over 2, or is a 0, right? So this thing, a units along the x-axis, this unit's at x units. So how far is this? X plus a. X minus a, is that what you said? Yeah. Okay, so if the distance is x minus a, that's what we're going to put here for r. And what's the distance from minus q to there? It's x plus a, isn't it? So don't you get isn't this it? That's 4 pi k q times 1 over x minus a minus 1 over x plus a. Right? So now what's 1 over x minus a over 1 plus a? Add the fractions. Of the denominator is going to be x minus a times x plus a. And this is what we're going to get. And algebra isn't really obvious to you. You need to think about it until it is. Okay. And how does this simplify it? Okay, we're stumbling over algebra and we really couldn't be. This gives you 2a over x squared minus a squared. Okay. And the potential is approximately 2a over x squared. Up to 2a over x squared. And it's 0 on the y-axis. Now this is for a dipole oriented along the x-axis. Okay. Between the x-axis and the y-axis, it goes like a cosine. So if you're oriented here at angle theta, it's kind of going to be this times the cosine of the angle. And there's a dot product definition in terms of the dipole moment you're going to see. Now this is next week, but I'm anticipating next week. So you'll take a good look at the stuff with the potential, what you're going to need for the midterm test. Okay. And for what we do next week. Now, the other thing is, and I think
That's more of the
situation. Right now, I'm talking, I'm being a little vague about some of this stuff, doing a little bit of hand waving. I don't want to make it too rigorous at this point. Messed up my left shoulder. Really careful when I lift these things. We recording, we're recording this board washing. The other chapter we're going to look at next week is capacitance. You're going to want to review that. But it's pretty simple. If I've got, it's not always simple. Symmetrical capacitors are a little more involved than a parallel plate capacitor. If I got two plates, area A, at each of them, separation. Often we use little a for separation. Okay. But maybe you ought to use B so we don't confuse the A's. And charge density sigma. So we have plus sigma on one, negative sigma on the other. And that should be implicit. You should understand that from what you've already seen. Then the electric field in between Okay, so it's very easy. It's if you take one of the surfaces and put one of these little Gaussian surfaces around it, okay, where it intersects this thing, this little surface increment, you got same area here as you got over here as you got in the middle, right? By symmetry, the field has to be perpendicular as long as you're close to the, much closer to the plates than you are to the edges. We talked about that. Remember, we took the light meter over to the display, saw how the field or the light intensity doesn't fall off very rapidly. It stays pretty constant as you move, as long as you don't get too far, as long as your distance from the surface is much smaller than your distance from the edges. Okay, and you put that whole argument together, and you find that your field is perpendicular, so your total flux is 4 pi k sigma A. I'll use delta A so don't confuse it with the total area, the whole thing. That's your total flux through the ends, so that the total area from which the flux emanates, here are your field lines, the parallel to the perpendicular surface. Okay, you got area 2A of the field to exit. Make sense? Okay, so total area is 2 delta A. The field is 2 pi k sigma. That's the field due to one plate. Field due to the other plate is also 2 pi k times negative sigma, meaning it's going to align in between the plates and the fields are going to reinforce between the plates and cancel outside of the plates, which we demonstrated with the parallel plates and the, what was it? Something on a string that was bouncing back and forth, piece of foil or something. Okay. So we'll go back to that whole thing. If this one is positively charged, this one is negatively charged, the field's going to look like that. It's going to be 4 pi k sigma. So your potential difference is 4 pi k sigma d, right? Make sure you understand this when you come in next time, okay? Pretty simple, straightforward argument. Capacitance is the amount of charge you get per volt. A signal divided by four pi k sigma d is the A over 4 pi k g A epsilon naught over d. Check that with your textbooks derivation. Something doesn't quite feel right about that, but that's what it is. Total charge here is A times sigma the potential difference is electric field times your separation, 4 pi k sigma times d. Pretty confident of that, but something doesn't feel right. So check it out, okay? Also check out the sign of that potential. Scan through chapters of potential capacitance so you learn more when you come in next time, okay? And also look at those parts of the introductory problem sets, transition problems, that address this, because the better equipped you are, the better you know that stuff, the more you know. Okay, and it's kind of repetitive besides what I said before, but that's where we are. Okay. And you got 5 days between now and then, unlike the 2 days you've had since our last class. So, and I hope that you've made some progress on the sign problem.
I was gonna ask about
Oh, yeah, let me